So we're going to look a little bit into a certain kind of network measurement called traceroute. And if we think about the way that mapping software works, when we're trying to figure out how to get between a location that we want to visit and our starting point, we use software that tries to tell us the best way to get there. Maybe it tells us if there's going to be any traffic along that route, or if there's going to be construction, and it may suggest alternate routes. If we look at a tool like the network traceroute, what it's telling us is something very similar. It's telling us the path along the network that we are going to be traveling when we're either sending or receiving information from a remote site. And we're going to be looking at this from two different directions. We're going to be looking at this from leaving from our machine or a machine that we may be on and trying to travel to a destination, as well as what it would look like trying to get back from that destination to us. And it may be the case that we take different routes to get between these two different things. So I'm going to be using a terminal window that's connected to a machine on ESNet that's located in Washington, D.C. And we're going to use the tool name. It's called Traceroute. And I'm going to be trying to evaluate the route between this machine and something that's located at Lawrence Berkeley Lab in Berkeley, California. And the name of that machine is nettest.lbl.gov. So when I type this command, it's going to be performing little tiny probes of network information to each of the hops, so to speak, along the path. And each of these hops represents a different network element, a router or a switch, that may be responding as we travel between these two different things. So as we leave the host in Washington, D.C., we land on our first hop router, which is also located in Washington. We also see that we visit Chicago, Kansas City, Denver, Sacramento, Sunnyvale, which is located in the Bay Area of California, until we finally get to the LBL domain, and then there's a couple of last little hops that take us in there. You'll notice that the entire path is about 64 milliseconds in terms of latency, and this gives us the route between this remote host and where we were physically located. So this gives us the first real indication of how we would travel between these things. Now let's say that we wanted to evaluate the route on the way back. To do this, we need to use the perfSONAR toolkit, and this is running on nettest.lbl.gov right now. If I open up this little window right here on the left-hand side, it's labeled reverse traceroute. It's going to, first of all, perform a traceroute between that host and my server that I'm using right here for this demonstration, which is on a wireless network. Once this is done, it's going to give us the opportunity to use a small window where we can enter in the address of a different host. So when it does the traceroute here, because I'm on a wireless network, we see that there's some blocking of this example, but that's okay. We're going to type in the address of our host in Washington, D.C. so that we can continue. And once we enter this in, we can perform what's called the reverse traceroute. And if we look here, this mimics what we saw with our forward traceroute. We exit the LBL network. We have two hops on routers here, and we take almost the same exact path. We leave through Sunnyvale, we go through Sacramento, Denver, Kansas, Chicago, Washington, until we finally get to the host on the other side. So this tells us two pieces of information. It tells us that the path is symmetric. It's the same for the forward and the reverse. And it also says that the latency number that we get here as a result, this approximately 64 millisecond value, is the same in both directions. So back to our example of if this was a piece of mapping software, we're taking the same route to get between these two different locations.